All right, welcome to Physics Video 7.8. We're going to be learning about basic electric circuits and electric power. The objectives are listed here on the screen, so take a second and jot them down. Please be aware there is one new equation down here at the bottom, specifically the equation for power. So here we go. All right, circuit diagrams. Up until now, I've been drawing my circuit diagrams by drawing a little battery and a light bulb. Okay, that's not going to work anymore. So we're going to start using symbols for them. Okay, so the symbol for wire is basically just a straight line. It's not rocket science. A battery, instead of drawing a battery like this, we're now going to draw a battery like this. Okay, notice the battery has a negative side and a positive side. The current flows, if you imagine this little symbol looking like an arrow, then the current flows in the direction of the arrow. And basically all that's happening there is the electrons are flowing out of the negative side of the battery and being attracted to the positive side of the battery. Okay. It's also worth noting, or remembering, I guess, hopefully, that the negative side of the battery represents the side with a high amount of electric potential, and the positive side of the battery represents the side with a low electric potential. Okay, and all that's happening is the electrons are trying to go from high potential to low potential. All right, and finally, we're going to replace our light bulb with the symbol for a resistor, which is the squiggly line. It looks sort of like Bart Simpson's head, if you're a Simpsons fan. It doesn't matter how many squiggles you draw, just need to draw a squiggly line. That symbol is the symbol for any resistor, whether it's a light bulb or a motor or a buzzer or something. And the important thing to know about resistors is all resistors do the same thing. They take electric potential energy from the battery and then convert it to some other form of energy. In the case of a light bulb, it's converting it to light energy. In the case of a buzzer, it's converting it to sound energy. In the case of like a heating coil, like you might find in a toaster, it's creating heat energy, obviously. A motor converts the electric potential energy to kinetic energy. That's why, that's what would make like a little toy car go, is having an electric motor in there. Okay, so anyway, regardless of what the device is, it is a resistor and it controls the flow of electrons. Okay, so there we go. And notice this is the three things that you need for an electric current, right? You need something to carry the wire, or something to carry the electric current. Would be analogous to the pipe for your water, right? You need a battery, something to provide voltage, and you need a light bulb, or some sort of resistor to control the flow of the electrons. Okay, so here we go. The simplest possible circuit that you can have has to have all three of those things. You have to have a voltage source with your positive and negative side. Oh, try that again. With your negative and positive side. You have to have some form of resistor. So here's our resistor up here at the top. And then finally, you have to have a closed path that connects the high ZP, high electric potential, to the low electric potential. So here's my path. It's going to just go around like that. Notice it doesn't matter where the resistor is. This drawing here on the bottom is the exact same thing, because in both drawings, the electrons have to come out of the battery through a resistor before coming back to the battery. Same thing. Electrons come out of the battery through a resistor before coming back to the battery. Okay? All right, so next. Oh, that's not what I wanted to do. Let's try that again. Boom. So here's a graphic of the same kind of thing, basically. Here we've got our voltage source. Here's our resistor. Okay, so if we wanted to draw this using a circuit diagram instead of, this actual drawing here, we would draw it like this. We'd have our resistor up here at the top, and that would be connecting our battery. Now, before I draw the battery, think about which side is going to be the long side and which side is going to be the short side. There's two ways to think about it. The electrons are coming out of this side, which makes this the negative side, and this is the positive side. Or the current is flowing that way, which means my battery actually has to go this way. Okay? So, there you go. It's also worth noting that it doesn't matter where the light bulb is. So, I'm not going to worry about trying to rebuild this, but that I can, you know, do this. None of this matters because no matter where I put the light bulb in the circuit, the electrons have to go out of the battery, through the bulb, and then back. Okay, so there we go. All right, so incomplete circuits. I don't know if you can read this, but it says incomplete circuits. And it basically gives us some examples of things that can go wrong with circuits. So here they are. The first thing that can go wrong is you can have what's called an open circuit. An open circuit is a circuit that does not have a closed path to carry the current from one side of the battery to the other. All right, so that would look like this. Right now, these circuits that I've drawn are fine, but as soon as I do this, boom, now there's a gap in the wire, and that's going to make it so that the electrons are no longer drawn from the negative side to the positive side, right? And so the current's not going to flow. And it doesn't matter where the gap is. The gap could be here, or here, or over here, or here, or anywhere along here, even in the middle of the resistor, which is actually what happens when a light bulb burns out. And same thing down here. You can have a gap anywhere down here, okay? Now, to equate that to our little thing here, that would be like doing this. Let me see if I can get this to work. Boom. Let's put a gap anywhere in our circuit. If I put a gap right there, the electricity stops flowing, right? The electrons are no longer being drawn from the negative side to the positive side. Okay, so that is an open circuit. Let's connect it back up. Boom. All right. The next issue you can have is what's called a short circuit. All right, a short circuit has at least one path that allows the current to get from high electric potential to low electric potential without encountering any resistance. So the easiest example of that would be this. Look, my electrons are coming out of this side and going into this side, but there's nothing preventing their flow. So this is going to cause it's basically just going to drain the battery almost infinitely quick. And my electrons are just going to go, and they make that sound. And so you get basically an infinitely high current since there's no resistance, right? So that's going to kill your battery. This one over here is actually the one that happens more commonly. So this might be a battery trying to power a light bulb, but we've got what you'd say is a short in the circuit, okay? And so what's going to happen is, let me clear this up a little bit, the electrons have a choice. The electrons are going to come out of here, and they get to here, and now they have a choice. They can either go this way, where there's resistance, or this way, where there's no resistance, right? And so electrons, as is true with most things in nature, tend to take the path of least resistance. So the electrons are just going to go this way, and for all intents and purposes, this resistor might as well not even be here, okay? This third drawing over here is basically the same thing, just drawn a little bit, you know, more creatively, we'll say. So the electrons are going to come out, they get to this junction here, they can either go this way with high resistance, this way with low resistance. They take the path of least resistance and do this. Once again, this path is doing nothing for us. Okay, so let me see if we can give you a video of that. Oh, I passed it. So right now, our battery is working just fine, or our light bulb is working just fine, but let's put in a short. So what we're going to do is we're going to put in another path with no resistance, and watch what happens. All right, so a little bit overly dramatic. The battery has burst into flames, but what that's trying to show you is that the electrons can't keep up with the flow that they need to. The electrons are coming out of the battery sort of infinitely fast. Notice there is no flow through the light bulb because all of the electrons are taking the path of least resistance instead of going this way. Okay, so there you go. So that's a short circuit. And then the last thing is a voltage. So if you have no voltage source, then obviously nothing's going to work, right? If you take the battery out of a flashlight, the light's not going to go on. All right. I don't think I need to show you the graphic of that. If you are confused, then ask me in class. But you have to have a battery to push the electrons, right? Otherwise, the electrons will just sit there in the wire and be happy hanging out. All right. Last thing we need to talk about is what's called power. This is electric power. Okay. Well, any kind of power, really. All right. So power. Symbol for power is a capital letter P. Remember, lowercase p is momentum. So capital P, power, is the rate at which energy changes. Okay. When we did work and energy, one of the equations that I sometimes teach, but didn't this year because there's not enough time, is this. To find the power something generates or uses, you take the amount of work that it does and divide it by the time it takes to do that. So remember, work is basically a change in total energy. Divide that by your time. So there's your equation. All right. And it's measured in watts. Okay. Notice watts is spelled W-A-T-T-S. And a watt is defined as a joule per second. That is super huge, super, super important. 1 watt is a joule per second. All right. And this example should help clarify it. All right. It says a 60-watt light bulb. Really, a 60-watt light bulb is a 60 joule per second light bulb, which means that it uses 60 joules of energy every second. So every second you've got that 60-watt light bulb in. Every second it uses 60 joules of energy. And then it converts it to light and heat energy. Okay. There's a little note down here at the bottom that says that's only true if you plug it into a US outlet. If you take a 60-watt light bulb to Europe, it actually uses, I'd have to do the math, but I think it uses more power because they have higher voltage there. So there you go. I might be wrong about that, about the more power. I'd have to do the math. Okay, so how do you find power? Well, it turns out that when you're talking about electricity, the amount of power, whoa, that was not what I wanted to do. The amount of power is just the current times the voltage. Okay, so let's do a quick example. You're going to look at this example and you're going to go, well, duh, that's easy. But I also want to talk about the units. All right, so here we go. Here's our example. A 9-volt battery is used to power a light bulb that draws a current of 0.60 amps. How much power is it using? So here's what we know. We know the voltage is 9 volts. We know 0.60 amps is the, stop and think, what do we measure in amps? Current. And we want to find the power. So P equals I times V gives you, I'm going to write it up here. You'll see why in a second. 9 volts times 0.6 amps equals, and so you can multiply that out and you're going to get 5.4. I've already told you the answer is going to be watts. But let's talk about why. You hopefully remember, and if you don't, this is worth writing down, that a volt is the same thing as a joule per coulomb. Okay, and similarly, hopefully you remember that an amp is the same as a coulomb per second, right? Because it's how much charge, how many coulombs go through your wire every second. So there's my units, and notice when you multiply this out, coulombs cancel out, and you're going to end up getting 5.4 joules per second, which I've just told you is a watt. Okay, so there is your power. Okay, so every second that bulb is on, it's going to use 5.4 joules of energy. All right. All right, one last example. Remember, we've now got 2 equations that have current and voltage in them. So here's the new one. Whoa. But remember, we've also got this one. Okay, so in this problem, it says a 30-watt light bulb, so it's giving you the power. It says it's intended for use in a 120-volt power outlet. So we know the voltage is supposed to be 120 volts. And the question is, what's the resistance? Whoa. So you look at this, and we don't have an equation over here for resistance, but we do have this. So I should be able to find the resistance if I can figure out the current and the voltage. The voltage I already know, so I need to find my current. So it looks like I can use this top equation to find it, right? So in other words, if P is equal to I times V, divide both sides by V to find out that V is P over I. No, that is not what I want to do. Edit, edit, edit. I'm sorry, we're trying to find I, aren't we? We're trying to find I, so divide both sides by V to find that I is P over V. So let's see, we've got a 30-watt light bulb plugged into 120 volts. So our current there turns out to be 0.25 amps. So now we can find our resistance. So let's extend our page a minute. Okay, so let's switch colors here. So now what we know is we're trying to find our resistance, right? So V equals IR, divide both sides by I, and that's going to mean that R is V over I. So our voltage is the 120 volts that is customary in American power outlets. Our current we just found at 0.25 amps. Grab your calculator, divide it out, and you get 480. Hopefully you remember the units for resistance are ohms. All right, so there you go. Power and basic circuits.